Hey everyone, welcome to this explainer. You know, if you've ever wondered how scattered, messy data all across the internet somehow magically comes together to give you exactly what you asked for, well, you are definitely in the right place. Today, we're going to completely demystify SQL Joins. We'll look at the hidden logic behind the scenes that manages all that scattered data, turning a chaotic pile of puzzle pieces into a perfectly clear picture. Okay, let's dive right into this. Here is our roadmap for today. First, we'll look at connecting data with joins. Then, we'll set up some student and course tables. After that, we're exploring the primary joins, understanding the self-join, and finally, looking at real-world database applications. All right, Section 1, Connecting Data with Joins. Let's get a handle on the core concept. Think about professional databases for a second. You don't just dump all your information into one giant, overwhelming spreadsheet, right? That would be totally chaotic and incredibly inefficient. Instead, data is neatly separated into distinct, organized tables. But to actually use that data, we need a way to seamlessly stitch it all back together. So an SQL join is simply the method used to combine data from two or more tables based on a related column. It helps retrieve all that connected data. If you are working in SQL or any database management system, this bridge is absolutely one of the most crucial concepts you'll ever learn. Moving on to Section 2, Student and Course Tables. This is where we set up our sandbox. To really wrap our heads around how these joins work without suffering from cognitive overload, we're going to use a sandbox, just a simple, recurring set of data. Here is our first puzzle piece, the student table, with two columns, student ID and name. Meet our recurring characters for today. We've got Rahul with ID 101, Aman with 102, and Priya with 103. Keep them in mind. Now let's bring in the second puzzle piece, the course table. Here we have student ID and course. 101 is taking DBMS, 102 is taking Java, and 104 is taking Python. So the crucial point here is that both of these tables share one common column, the student ID. That shared column, that is our anchor. It's exactly what we will use to perform our joins and actually combine the data. Section 3, Exploring the Primary Joins. Let's look at the four main types. We're going to kind of take a menu approach here and step through the variations, starting off with the inner join. Now, this is the most commonly used join in all of SQL. You can think of it like a really strict filter. It looks at both tables and returns only the exact matching records. If a record doesn't have a perfect match in both the left table and the right table, it just doesn't make the cut. And this brilliantly illustrates how that looks with our sandbox data. Notice we only see Rahul and Aman. Why is that? Well, because Rahul's ID, 101, and Aman's ID, 102, are exact matches that exist in both tables. Priya and the Python course, they get filtered out entirely because they didn't have matches on both sides. But what if we don't want to be that strict? Conceptually, let's look at the left join versus the right join side by side. Sometimes you kind of want to favor one side of your puzzle pieces over the other. A left join essentially says, hey, give me absolutely every record from the left table, regardless, and only the matching records from the right. A right join just completely flips that logic. It says, give me all the records from the right table and only the matching records from the left. Let's see that left join in action. Because our student table is acting as our left table, every single student gets a VIP pass to the final output. Now, what's really interesting here is Priya in the third row. She gets included, but she hasn't actually picked a course yet. Because no match was found on the right side, the database essentially just shrugs and fills in that blank with a null value. All right, now let's flip it and look at the right join output. This time, the course table on the right is getting the preferential treatment. Every single course must be listed. So we see DBMS and Jana with their respective students. But look at Python. The Python course shows up because it's in the right table, even though student ID 104 is completely missing from the left student table. Because of that, the student name attached to Python is simply null. Next up on our menu is the full join. And this one is exactly what it sounds like. It is the ultimate combination. It returns all matching and non-matching records from both tables. It grabs the matching inner records, the left unmatched records, and the right unmatched records. The whole shebang gets pulled into one massive unified view, with nulls filling in any of the gaps on either side. Moving on to Section 4, Understanding the Self-Join. This is kind of the odd one out. So far, we've been joining completely different tables together. But the self-join requires a total shift in how we think. It is literally used to join a table with itself.
Now, why on earth would you do that? Well, it's incredibly useful for comparing rows within the exact same table. The classic example is mapping out employee and manager relationships. Think about it. A manager is also an employee, right? So instead of making two separate tables, you just keep everyone in one unified employee table and use a self-join to link a manager ID right back to an employee ID.
Finally, Section 5, Real-World Database Applications. Let's look at the big picture. Let's move past the raw syntax for a minute and see how this builds into something much bigger. But real quick, let's do a rapid-fire revision of the 5 rules to lock them in. Ready? Inner gives matching records only. Left gives all left records. Right gives all right records. Full gives absolutely all records. And self joins a table with itself. So why does this all matter? Well, because SQL joins are practically the backbone of almost every major industry out there. Banking systems use them to connect your specific account with literally millions of transaction records. E-commerce platforms link your shopping cart to vast, complex inventory tables. School management systems connect massive student bodies with schedules. And hospitals securely tie patient records to doctors and appointment histories. They absolutely rely on this logic to efficiently retrieve related data and manage massive amounts of complexity.